Hello everyone, this is Seohyeon. Today I'm walking you through subset selection from ISRP chapter 6.1, and I will wrap up by solving problem set 5 like an instructor. The plan is simple. We will see why training error is not the goal. We will compare best subset, forward and backward selection. Then we will learn how to choose the model size using cross-validation and validation. Finally, we will answer the problem set questions and end with practical tip you can reuse. Our goals are straightforward. First, understand what the three selection procedures do and when to use them. Second, learn to pick a model size by minimizing test error using cross-validation. Third, apply all of this to problem set 5. The main message is don't optimize training error. Always ask how will this perform on new unseen data. Cross-validation gives us that answer. Let's set definition first. Training error is the error on the data we use to fit the model. In regression, we often summarize it with the training RSS, residual sum of squares. Important fact, if we keep adding predictors, the training RSS can only go down. That's because a more flexible model can always fit at least as well as a simpler one. But this is exactly why training error can misread us. More flexibility can start to minimize noise. What we actually care about is the test error, meaning performance on new data. Since we don't have infinite new data, we estimate test error using a validation splitter, K for cross-validation. Think of cross-validation as practicing with multiple mock exams that mimic the real test. Uh, Here's the big picture. As we increase model complexity, testing error and training error goes down steadily. In contrast, the cross-validation error usually shows a U-shape. It drops at first as we fix underfitting, then rise again when we overfit and start fitting noise. Our objective is therefore to minimize the cross-validation error, not the training error. If the bottom of the cross-validation curve is fairly flat, we will also apply the one standard error rule. Choose the simplest model whose cross-validation error is within one standard error of the minimum. That gives us stability and interpretability. Now, the three procedures that guarantee candidate model. This is the brief explanation of the subset selection. First, best subset selection checks every combination of a given size for a fixed number of predictor, say size k. It evaluates all combination of k predictor out of the four standard stand, picks the model with the smallest training RSS at the size. It is training optimal at the size, but it is expensive overall because across all sizes there are 2 to the power p total models. Also, the winner at size 1 and size 2 do not have to be nested. They can be completely different set. For stepwise selection starts from the empty model and adds the one predictor at a size, always choosing the next predictor that improves your criterion the most. It builds a nested path, meaning the model with k predictors is contained in the model with k plus 1 predictor. It is much cheaper, roughly on the order of p squared feet, and it works even when you have more predictor than observation. The limitation is that it is greedy. It can miss pair of predictor that only work strong together. Backward stepwise selection starts from the full model, remove one predictor at a time, and also create a nested path, but in the reverse direction. It has similar computational cost, but it requires a stable full model fit. So you can typically need more observation than predictor to even start. It is also greedy. An only bad remover can block a better combination later. The key idea is these methods guarantee the candidate model. We will choose among them using cross-validation. So first, to make best subset concrete, imagine just three predictors. When the size is 1, there are three one-variable candidates. When the size is 2, there are three two-variable candidates. The best one at size 1 might be only the second predictor, while the best at size 2 might be the first and the third predictors. Notice the jump. The size 1 winner is not necessarily contained in the size 2 winner. That's normal for best subset. In higher dimension, the total count of model grows explosively, 2 to the power p, so best subset is training optimal but often computationally impractical. The usual workflow use any of the three procedures to create a sequence by size, then choose the size by cross-validation. Forward stepwise is popular because it is fast and stable when the number of predictor is large, and even when we have more predictor than observation. The procedure is simple to explain to teammates. Each step, try adding each remaining predictor, pick the one that helps the most, and repeat until your stopping low. Each main caveat is the greedy nature. It may miss a pair of predictor that is weak individually but strong together. That is why we don't finalize based on training error. We will evaluate each side by cross-validation and then decide. Backward stepwise works in the opposite direction. Start with the full set of predictors, then drop the rest helpful one each step. It gives a clean nested sequence but needs a reliable full fit model fit. So it is not a good choice when you have more predictor than observation or serious numerical instability. Just like forward, it is greedy. It does not guarantee the best training model at a given size and certainly not the best test model. Again, this is why we learn on cross-validation or for the final choice. Here is the workflow I actually use. First, do k-fold validation, say 5-fold or 10-fold, both are standard. Split the data into k parts for each model size, and for each fold, fit the model on the other k minus 1 parts and measure the error on the held part. Average those errors across folds to get the cross-validation error for this size. Second, choose the size with the smallest cross-validation error. If the bottom of the curve is flat, apply the one standard error rule. Among the model whose cross-validation error statistically indistinguished from the minimum, pick the simplest one. Two practical reminders. One, no data leakage. Any scaling or feature engineering must be fit inside the training fold and then applied to the validation fold. Two, for classification tasks, use stratified fold so the class balance stays stable across folds. When cross-validation is expensive, I check information criteria as fast surrogate. Mallow's CP behaves like an estimate of test mean squared error for ordinary rest squares. Think training error plus a penalty of 2 per parameter. AIC, read it as AIC, also uses a penalty of 2 per parameter and for ordinary rest squares. Tend to rank model similarly to CP is a good prediction-oriented choice. BIC uses a heavier penalty that scales like the number of parameters times the log of the sample size. So as the dataset gets bigger, BIC favors smaller, more parsimonious models. Adjusted R² is maximized. It corrects for the fact that plain R² always increases when you edit variable. In practice, I compute these for along the model sequence and also look at the cross-validation curve. When they point to the same sides, that give you a strong defensible discussion. For the problem set A, question: which method guarantees the training optimal model for a fixed size? The answer is best of selection, because at the given size, it evaluates every combination and picks the lowest training model. Forward and backward only explore one greedy path each so they can mix the best one and decide. But remember, training optimals, not test optimal. We will still choose size by cross-validation. For problem set 5b, the question across best subset, forward and backward, how do we pick the final model and the size? Is any method guaranteed to minimize test error? The answer is none of these procedure guarantees the smallest test error. Therefore, we must estimate test error with validation or k-fold cross-validation, and we choose the size with the smallest cross-validation error. If several models are effectively tied within the uncertainty band, we use the one standard error rule and pick the simplest model in that band. For problem set 5c, for statements 1 about forward selection, the model with k predictor is contained in the model with k plus 1 predictors. That is true. Forward add one predictor at a time and never remove any, so the sequence is nested. For statement 2 about backward selection, the model within k predictor is contained in the model with k plus 1 predictor. That is also true. If we think of the sequence in reverse, backward removes one predictor at a time. So when you go from the size k plus 1 down to size k, you simply drop one predictor. That means the size k model is contained in the size k plus 1 model. And for statement 3, the size k model is contained in the size k plus 1 model from forward. Fourth, the two methods follow different greedy paths, so there is no nesting guarantee across methods, and the counterexample is like below. Statement 4, the size k model from forward is contained in the size k plus 1 model from the backward, and it is also false for the same reason. Statement 5, the best subset winner at the size k is contained in the model subset winner at size k plus 1, and it is also false. Best subset winner do not need to nest across sizes. They can jump as the size changes, and the counterexample for p equals 3, best at k equal 1, it can be different from the k equal 1 and k equal 2, like below. Takeaway, within forward and or within backward, you get nested sequences across method or across size for best subset. Nesting generally does not help. Let me close with four practical tips you can use right away. First, select by cross-validation. Use 5 or 10-fold cross-validation. Plot cross-validation error against model size and choose the same smallest error. If the minimum is flat, use the one standard error rule and pick the simplest model within the band. Second, standardize your feature, especially if you plan to use REACH or LASSO, because penalties are sensitive to scale. Standardization also helps stability and interpretability in selection paths. Third, respect heritage. If you include an interaction term or polynomial term, also include the corresponding main effects. It keeps the model interpretable and behave better outside the observed range. Fourth, when you have more predictor than observation or when predictors are strongly correlated, avoid backward selection. Prefer forward selection or penalized method like REACH or LASSO, like as I said before. Lastly, key conclusion. Adding variable always lowers training error, but it does not guarantee better test performance. Expect a U-shaped test error curve. Best subset is training optimal at a fixed size, but can be computationally heavy and non-nested across sizes. Forward and backward are fast and nested but greedy. They can make synergetic combination. After you pick a model size, refit on the for training data with the variable and report the cross-validation on error and adjusted R², along with the short interpretation and your random seed for reproducibility. Pick the smallest model whose cross-validation error is within one standard error of the best. Thanks for watching. Hope this helped you build models that perform beyond the training set. Thank you.